This is lesson 10.1, graphing square root functions. You should be on page 544. In this lesson, you will learn how to graph a square root function, how to compare square root functions using average rates of change, and how to solve a real-life problem involving a square root function. First of all, what is a square root function? A square root function is a function that contains a square root with an independent variable in the radicand. So if you're like, what is that? Well, it's basically saying a square root function is a function that has x underneath the radical. The parent function for the family of square root functions is f of x equals square root x. So remember, the parent function is the most basic function of, or the most basic, I guess, equation of that type. So f of x equals square root x would be the most basic square root function, so that's called the parent function. So I'll just underline that there. The domain of the parent function is x is greater than or equal to 0, and the range of the parent function is y greater than or equals 0. And you can see that in the picture here. Maybe we should talk about, before we go on with domain and range, let's look at graphing the parent function. The parent function is easy to graph, so let me just quickly make a table. And, you know, when you have a radical, let me write down the parent function. First of all, we cannot plug a negative number in there. I can't take the square root of a negative. So I could plug in 0, because the square root of 0 is 0. Let's use our perfect squares. I could plug in 1, and the square root of 1 would be 1. And if I plug in 4, the square root of 4 is 2. Now you might wonder, why didn't he plug in 2? Well, think. If I put a 2 in here, do you know what the square root of 2 is off the top of your head? And I hope you're thinking, no. We want to use perfect squares. So 0, 1, 4, 9 is a perfect square. The square root of 9 is 3. And now let's graph this. 0, 0 would be here. 1, 1 means 1 right, 1 up. 4, 2 means 4 right, 2 up. And 9, 3 would be 9 right, 3 up. And what you're getting at, that's a square root function. It looks like a half parabola opening to the right. You might want to write that in your notes because that could be a good audit question. What does a square root function look like? It's a half parabola opening right. Okay, so you might want to put that in your notes right now. The value of the radicand in a square root function cannot be negative. So again, what that's saying is I can't have a negative underneath a radical because it gives you no solution. It can't be calculated. Okay? So whatever expression is under the radical must be greater than equal to 0. That's what that statement that I highlighted in yellow is telling you. Underneath the radical, that must be greater than equal 0 at all times. Okay? So let's look at the sample. Describe the domain of f of x equals 3 times radical x minus 5. So x minus 5, I'm just going to point to what I wrote. X minus 5 must be greater than equal 0 because I have to have 0 or a positive number to take the square root of. So let's find the domain. Add 5. And if I do that, x would be greater than equal 5. So the domain of this function would have to be x values that are greater than or equal to 5. That's how I can find the domain of a square root function. It's pretty easy. Just make sure that anything under the radical, that statement must be greater than equal 0. Why don't you pause the video now and try questions 1, 2, 3. I'd like you to find the domain of the function listed. These are square root functions. Go ahead and do that. And I'm back. So the domains would be, for the first one, you can see x greater than equals 0. Same for the second question. I can plug in 0 or anything greater, and that would give me positives here. Now for 3, you got to be careful. I'm going to use my highlighter. This statement must be greater than or equal to 0. So you can see I wrote that out. So I got to solve that. take away 1 from each side, negative x is greater than or equal to negative 1. Now I have to divide each side by negative 1, and remember, when I do that, I have to flip my inequality around. That's when my inequality reversed. So x would be less than or equal to 1. That would be the domain for this particular problem. I can only plug in values for this that are less than or equal to 1. A radical function is a function that contains a radical expression with the independent variable in the radicand. So we've kind of talked about that already. That's a fancy way of saying, when you read that, I have a radical and x is underneath the radical. That's what independent variable in the radicand means. X is underneath the radical. A square root function is a kind of radical function. So when you hear radical function, a square root function is part of that family. Now this chart is going to show some things that we've already talked about this year on numerous occasions, so it's good. This should be a review. You can transform graphs of radical functions in the same way you transform graphs of previous functions. Okay? So, remember, when you have horizontal transformations, horizontal would be inside the radical, and it's going to be opposite of what it seems. Like when you look here at these samples, look at this. This says minus 2 inside, but that means move your function 2 right. Or you see plus 3, that actually means go 3 left. Or horizontal stretch or shrink. You see how we're multiplying by 3 inside. Now multiplying by 3 makes you think it's 3 times bigger, but when it's inside it's reversed basically. We're shrinking by a factor of 1/3. Or if you see here, we're multiplying by a half. Normally multiplying by a half makes something half as large. When it's inside, that's actually going to stretch your graph horizontally by a factor of 2. That's all review. Remember, vertical is outside. Vertical's normal. So when you see outside adding 7, that's moving my graph up 7. Or minus 1, moving it down 1. Or here, multiplying outside by 4 stretches my graph by 4, or if I multiply by a 5th, it's going to shrink my graph by a 5th. Negatives will reflect the graph. If the negative is outside, that's a vertical. I can put a vertical reflection. If it's inside, that's a horizontal reflection. Okay? Now that we talked about that, I think we can look at this. Graph f of x equals square root x plus 3, describe the range. Now, I would let you use your calculator to do this, but this is what I'd really like you to know, okay? Let's think about the parent function. F of x equals square root x. I quickly plotted the parent function. Remember, the parent function would have the points 0, 0, 1, 1, 4, 2, and 9, 3. I did that already in the video. Now, plus 3, that means take this function that I'm highlighting and just move it up 3. So you notice, look at these points. You notice this point is 1, 2, 3 higher, and this point is 1, 2, 3 higher, and this point is 1, 2, 3 higher, and that's 1, 2, 3 higher. There's my new function. So this function is 3 units higher than the parent function. Now describe the range. You can see the range in my picture. Let me take a highlighter. I'll use a blue highlighter. Do you notice how the function that I created is always here and above? You see how the lowest it is y equals 3, and it's constantly above y equals 3. That's why the range is y greater than equal negative, or y greater than equal positive 3, I meant to say. Y greater than equal positive 3. Okay? This is a cool little website you might want to get out and play with as you watch the video. And you can see it here typed in. This can allow you to compare graphs really easy on your computer screen. So why don't we do the next example, or the next where we go to the bottom of page 544. Let me actually go back to that for a second. And I normally tell you to pause the video and try these. Let's do these on that site, and you can actually see what's going on. So for number 4, g of x is the square root of x minus 4. Does it make sense that that should move my graph down 4? Well, let's actually see that in the picture. And this first one I'll type in with you, so I'm going to type in y equals square root, got to find the square root x, and you can see there's the parent function. And now for the second function, remember it was y equals square root x minus 4. Let's type that in. Y equals square root x and then minus 4. And you see how this is 4 units lower. So this is kind of a cool sight. You can actually see what's going on. Okay? Let's go to question 5. So let me erase that out. There's the parent function. Question 5 is y equals the square root of x plus 5. And you can see that, let's go back to that. There it is, right there. Okay? Let's do that one on our calculator. Okay, so y equals square root x, and we said plus 5 under the radical. And can you see how this got shifted 5 left? You can count. 1, 2, 3, 4, 5. Look at this point. 1, 2, 3, 4, 5. Every point was shifted 5 left. Pretty easy. And then the final one for question 6 was n of x equals 5 times radical x. So that should stretch my graph by a factor of 5. Let's see it. Y equals 5 radical x. Look how stretched out that is. In fact, look at this point here. 1, 2, 3, 1. So let me start again. 1, 2, 3, 4, 5. You can see it's 5 times higher. This is at 2, and that's at 10. 10 is 5 more than 2. So you can see it's stretching it by a factor of 5. So it should be easy then to talk about the domain and range of each. So going back to number 4, when we had the square root of x and then minus 4, it should be easy to name my range. Can you see how this graph is always higher than negative 4? So the range here would be y greater than equal negative 4, for example. Okay? So I would encourage you to maybe write this website down, and if you have any questions, you can type these in and just get a feel for them. And it's pretty easy to pick up the patterns and how they transform, you know, if you're adding or subtracting inside the radical or multiplying outside and so on. Ultimately, the book is trying to get you to be able to describe the transformations of the parent function to the new function and graph it without even using your calculator. So I think we'll do that on this one here together. I'll show you how we can do it without. First of all, g of x is negative 2 times the square root of x minus 3 minus 2, and they want me to describe the transformations from the parent function to that. So it should be pretty easy. Do you see how there's minus 3 inside? That means move the graph right 3. So that's the first thing you're seeing. The minus 2 outside means to move the graph down 2. Okay? And you can see that, moving it down 2. And then the negative 2 means a couple things. It means stretch by a factor of 2, and it also means reflect. I just described the transformations. Now let's actually graph that, and I'm not going to use my calculator to graph it. So here's the parent function, and this is what I want to graph. So follow along with me. I'm going to take a blue pen. So ready? It says reflect and stretch by a factor of 2. So this point at 0, 0, it's not moving. It's on 0. 0 times anything won't move, but these other points that are not on 0 will. So negative 2 means double and reflect. So if I take 1 and double it, I get 2, and I reflect it, it's here. Okay, I'm going to put a little mark there. Okay? And then this point, double it and reflect it. So that would go to 4 and reflect it down to negative 4. And then this point, double it from 3 to 6 and reflect it down here to negative 6. And now there's one more thing. Remember here, this means right 3 and down 2. So take each of these points and go right 3 down 2. So this point, right 3, down 2. I'll make it big now. This point, right 3 and down 2 here. This point, right 3, down 2. And this point, right 3, down 2. And if I connect those, that's what the function in our example, oops, I'm a little off there. That's better. That's what the function would be for example 4 for g of x. This would be a picture of g of x, and I didn't even use my calculator to do it. We did this in the prior chapter comparing average rates of change. So that should be pretty easy. Remember, a rate of change is like using the slope formula. So in this question, they have a model representing the velocity of a free-falling object on the moon. So that's what this little equation will do. G is the constant 1.6 meters per second, so I would just plug in 1.6 for G. And D is the distance the object has fallen. The velocity of a free-falling object on Earth is shown in the graph, and they want me to compare the velocities and interpret the rates of change from D equals 0 to 10. So let's do Earth first. You can see I need the point 0 because they have 0, so that would be 0, 0, and D is 10, so 10 looks like it's about 14. Got to use the slope formula, so I'll do 14 minus 0 on top, you can see that, there are my y's, and 10 minus 0 on the bottom is 10, and 14 divided by 10 is 1.4. That's the average rate of change on the Earth. And remember, this is a free-falling object. The average rate of change of that velocity is 1.4. Okay? Now on the moon, we can use our formula real quick. We had basically y equals the square root of 2 times g is 1.6. Okay, I need 0 to 10, so let's plug in 0. And you notice if I plug in 0, that's going to get me 0. So my first point on the moon is 0, 0. My second point, plug in 10. So I'd need 2 times 1.6 times 10, and then square root that. So let's do that real quick on our calculator. When I plug that in, I get 32, and then I got to take the square root of 32, which I'm doing right now, and I'm getting about 5.7. Okay? So when I do, when I plugged in 10, I got about 5.7. Okay, let's use our slope formula. Here are the y's, there are the x's. I got to do 5.7 minus 0 on top, which would give me 5.7 on top. 10 minus 0 on the bottom is 10. 5.7 divided by 10 is 0.57. So you can see on the Earth, the free-falling object is going to fall quicker on the Earth than on the moon. Now that should make sense. Think about it. Gravity on Earth is greater than gravity on the moon. I'm sure you've seen pictures of things, kind of people when they went to the moon floating around. We don't float around here. Gravity's greater on the Earth. To wrap up the video, they have us solving some real-life problems that would involve radicals. Okay, like here, the velocity of a tsunami can be modeled by this function where x is the water depth in meters. It says use a graphing calculator to graph the function at what depth does the velocity of the tsunami exceed 200 meters per second. Okay, so a couple things here. When you look at this equation, the velocity is the y value, so we need to find out when y is 200. Okay, that's what we're trying to figure out, when y is 200. Now they say to graph it, I think it's more efficient. We're going to use our table. We'll use a table feature on our calculator. So let's go ahead and type the equation in our calculator. And you can see I typed that in. Okay, and you can see on my app here, you can see that square root function. Okay, now I would use the table. So let's start our table. Let's start it at 0. And to start, I mean a tsunami, this could be big numbers. Let's have our table go up by intervals of 100. Okay, we've used that. We've changed it to tenths. Let's change it to hundredths. And now let's go to our table and let's start investigating. I am looking for when y is 200. Okay, so I'm going here. Still not 200. I'm getting there. It's taking a while. Okay, but not, wow, we're almost there, and around 4,000 or 4,100, is the answer. So now let's change our table. We'll start it at 4,100. We want to know when y is 200. So let's change my table now to 4,100. Let's make an interval now of, I think we can make an interval of 1. And now let's investigate. I'm looking for 200. I'm at the getting close here. Looking for the closest to 200. Looks like my answer is about 4,082. 4,082. And do you see how 4,082 then is matching what the book is saying? Okay, I have that right here. Okay, 4,082 would be about the depth of the water. Okay, that would be the depth of the water for a tsunami to exceed 200 meters per second in speed. So that's how we can use that. They also ask us to find the average rate of change. I've already talked about that, so I think I'm not going to go through that again. I don't want to make the video any longer than it is. I'm going to stop the video here. If you have questions, make sure you ask during class.